Joshua Aniken Acosta, and today we are going to talk about the transmission line model. We will just skip the definitions about the transmission line and proceed to the schematic diagram. So here is our schematic diagram. We have the source voltage, we have the source impedance, we have the load impedance, and lastly we have the transmission line. So here, the transmission line is composed of two conductors. So in particular, this transmission line is a coaxial cable composed of the inner conductor, which is connected to the source impedance, and the outer conductor, the cylindrical conductor, which is connected to the source voltage. Now let us focus on the transmission line. So here is the parallel wire representation of our transmission line. So we have two conductors here, and we also have the insulation or dielectric material. So these dielectrics can be rubber, air, vacuum, or any other materials that prevent the flow of electric current. So we will divide our transmission line into very small parts, and we will call those small parts as the differential sections of the transmission line, each delta z long. So the delta z here means that it is infinitesimally small, just like how we derive the rate of change in differential calculus. Now let us analyze one of the differential sections. So here is our differential section for the transmission line. So we have two conductors here, and even though it is a conductor, it still has internal resistance, no matter how small it is. And we will call that as the series resistance. So next we have a dielectric here, and even though it is an insulator, it cannot completely prevent the flow of electric current from one conductor to the other. Therefore, it has a very small conductance, and we will call that as the parallel conductance. Next, when there are changes in the current flowing in the conductor, it produces a magnetic flux. Here's the magnetic flux. So it produces a magnetic flux around the conductor, which further induces the EMF or voltage, which opposes the direction of the current. So we will call that property as the inductance. Lastly, we can observe the structure of the transmission line as a capacitor. So the conductors act as the parallel plate of the capacitor and with a dielectric between them. Therefore, the transmission line also has the property of capacitance. So this is the circuit diagram of the transmission line with its four parameters in consideration. And this is actually called a lossy transmission line. And if this is a lossy transmission line, what does a lossless transmission line look like? So here is our circuit diagram for the lossy transmission line. And this is our circuit diagram for the lossless transmission line. So as you can see here, the resistance and the conductance in the lossy transmission line is omitted in the lossless transmission line. The reason is that a lossless transmission line is also called as an ideal transmission line. And when we say ideal transmission line, it has the perfect conductor. So a perfect conductor has no series resistance, and when the series resistance is 0, then it is considered as a short circuit. And also, an ideal transmission line also has the perfect dielectric or insulator. And since the current flowing through both of the conductors is completely blocked off, then there is no parallel conductance. So when there is no parallel conductance, then if there is zero conductance, then it is considered as a open circuit. So for the lossless transmission line, we only have the inductive and the capacitive parameters here. So this is the end of my discussion, and thank you for watching.